me come to a sedan, and this is a very common drive cycle that is used in India called modified Indian drive cycle. This has been defined by various regulatory agency. It is a 20 minutes for cars, and it is a modified India drive cycle. It was a India drive cycle, and then they modified it by looking at actually how the vehicles travel. And if you find this, one thing again you see that it actually is driving. So, a lot of stop and wait, it drives then stops, drives and stops. That is a very common of the city driving pattern. So, this is a city driving, this is not highway driving. But you also see that occasionally it goes to 70 kilometer and even 90 kilometer per hour. So, this is a big difference between a four-wheeler. A four-wheeler does, when we for example, drive on IT highway, 80-85 kilometer per hour is quite common. You are also in the evenings and all that, you can go to 90 kilometer per hour. And of course, highway driving would largely be between 40 and 80-90 kilometer, that will be a different kind of drive cycle. But this drive cycle is also standardized. It was actually standardized for a petrol vehicle, but we are using the same thing for electric vehicle. So, once again we can calculate the incremental distance travelled, and you find that if you go through at, and this is only giving you velocity versus time, velocity versus time, that is all the drive cycle gives you. And from there you have to compute the acceleration. You find that integration of the, find the distance it travels, incremental distance, integrate it, comes to 10.7 kilometer. So, it is a standard 11 kilometer drive, 10.7 kilometer, you compare one vehicle versus the other. How much energy does it consume? Given this, you again take a sedan, we have taken a rough sedan, 1400 kg, rolling resistance is good, you put better tires in the four wheelers, drag coefficient is 0.4, projected area is close to 2 square meter, wheel radius is bigger 0.3 meters. Again we have assumed regeneration efficiency of 0.5, well we will keep changing that, and we then as we pointed out vehicle goes up to 90 kilometer. So, drag coefficient matters a lot, projected area matter a lot, remember these two parameters play a role, and again I calculate what is the energy efficiency. First I will just put that in the spreadsheet, the numbers, the velocity numbers versus every second, find the distance travelled, convert it into meters per second, find the acceleration, then find all the three forces, acceleration force, the rolling resistance force and aerodynamic force. I find the total force required. From there I compute torque on the one hand, I compute power on the other hand, integrate it to get the energy, and integrate the distance, incremental distance to get the total distance. And if I find here, if I look at this, the efficiency is coming to 815, well 815, again I see here the curves showing slightly different. I will check out all these things, maybe this is with 100% regeneration, this is with 50% regeneration, I think I have taken 50%, and the peak goes to a little bit above 815, actually should have gone to 750, but if I take 816 watt hour and I divide it by 10.7 kilometer, I only need 77 watt hour per kilometer. And if I do not take the with the 100% regeneration, it only consumes 60, 650, again not correct here, but I will double check these figures, 650 or watt hour, and that comes to 60.8 watt hour. Without regeneration it consumes 91. So, you can see 90, 76, 60. If I can get regeneration, I need much smaller battery. Between regeneration and without regeneration, watt hour per kilometer is 50% higher. I mean from the 100% regeneration is 50% higher is no regeneration. Why? Because you are going up and down, increasing the speed and going down, that is what you are doing, not travelling at constant speed, lot of acceleration and deceleration. Well, that gives us what do we need. It will give us, of course, this is not taking into account efficiencies. So, you have to add all of that. Reality, my vehicle consumes closer to 125 watt-hour per kilometer. It clearly tells me that there is something not right, because I am more or less given the data for my vehicle. I do not know whether the tire is that good, probably not as good, but I think the main difference is in the motor. It actually uses an induction motor. This is a version 1 of electric Verito. It uses a induction motor, which at high speed gives me all right efficiency, but at lower speed gives me very poor efficiency. And since most of the time I am actually travelling at lower speed, look at this, that is what the city drive does. On campus I always travel at lower speed, I do not even ever go to 50 km/h. It gives a very poor efficiency, and that is the reason. On the other hand, if you design a good PMSM motor, you can get very good efficiency. Okay. This is something that we learn from this. The other thing that we will see in a little while is that it is highly dependent on drag. Drag, why? Because we are going up to 90 km/h. Drag plays a very important role. If CD is reduced, efficiency goes down from 76.3, or probably I do not remember now whether it was done with 0 regeneration or 50% regeneration. I will double check that, but you can significantly reduce that. I will show you this number later on again. So, if I summarize my 4-wheeler, most energy consumed between 800 second and 1200 second. In fact, that is what you see. Most of the energies, actually energy consumed till 800 seconds is not very large. Most of the energy is consumed here. This is now between 800 seconds and 1200 seconds, what is happening? It is vehicle is going to look at between 800 seconds and 1200 seconds. This is the time the vehicle is going up to very high speed, 70 and 90 km/h. Now, 70 to 90 km/h, that is a time drag takes over, and that is reason most energy is consumed there. So, if I do not drive that speed, I should get very good energy efficiency. Okay. Yet 80 watt-hour per kilometer to 90 watt-hour per kilometer, even with an inefficiency, if I can get 100 watt-hour per kilometer, it is actually good. As I point out, motor inefficiencies we have to take into account. As I pointed out, if motors are designed for higher efficiency at higher speeds, at lower efficiency it may not be at lower speed, it may not have a good efficiency, and it will hurt you a lot. That is what actually is happening, and typical induction motor based vehicle is giving you 125 watt-hour per kilometer because of that. So, how important it is for you to design good vehicle. The other thing that will become very important, which we have not done, while we have calculated torque, we have not yet talked about how much torque is required and is the motor giving me sufficient torque. We have calculated what the torque is required. We have not done climbing, well, but even I have shown you how to calculate that, and in one of the home assignment I have told you, given you that when you climb and go down, what is the torque and energy required. So, the torque needs to be also taken into account in designing the motor. I will once again now take up one more thing, a low end electric trucks. Very similar to what we have done, except the requirements now will change. Fortunately, the GVW, the gross vehicle weight is very high. You are talking about 3,500 kg. Remember that for a 4-wheeler we took 1400 kg. That's, and this is a low end truck. This is not a high end truck with the material. Rolling resistance is very good. I deliberately make my tire very good. I spend money on tire. Why should I waste energy? Drag coefficient, well, can't do much about it. It's a large vehicle, so there will be a lot of drag, lot of projected area. Wheel radius is made higher, 0.4 meters. I have taken different regeneration efficiency. The vehicle is designed to go up to 90 km per hour, but it also travels limited extent on the highway. But we have taken this MIDC cycle, the same cycle that we did for 4-wheelers. So, it will mostly run at lower speed, once in a while go to the higher speed. So, something that you have seen between 59 to 89 seconds it travels. There is a acceleration requirement. This is something that we had not taken, but the acceleration requirement is in first 15 seconds it should be able to go to 60 km per hour. You will see that this does not impact the power or energy as much, it will impact the torque. And then from 60 to 90 seconds it should be able to go in 25 seconds, 60 to 90 kilometer per hour. This is kilometer per hour, I should have added that, I will make the change. These are kilometer per hour in 25 seconds. There is another very important parameter about the truck. What is the gradability? So, I have taken 12%, it should be able to do at 30 km per hour. Now, that is again will impact the torque quite a bit, but not just that. Suppose it is on a slope, sometime you are traveling on a slope, say 12%, but then you need to park. So, you actually move around, there is a small thing much higher and you go and park there. Now, at 20% gradient, it should be able to start. We are not talking about 30 km per hour, we are talking about 0 or 1 km per hour. It not only has to start, but also has to do a little bit of acceleration. If it does not accelerate, it will never reach, never increase its velocity. So, small acceleration, let it take time for it to start moving. That is additional requirement that we have put, and we have put auxiliary system load of 20%. So, some of these things will impact the torque, we have not done too much, but the first level we will come back to this vehicle again and again, this specs this vehicle. But what I have done is I have taken the same MIDC cycle, same distance of 10.7 kilometer, no slope, I have not taken slope into account, and I have actually calculated the energy requirement. And you find that with 30%, I have done it for 30% regeneration and I have done it with 100% regeneration. At 30% regeneration, this number is right, 2603 watt hour it consumes, 10.7 kilometer, it consumes close to 243 watt hour per kilometer. This is a much bigger truck, and if I take 100% regeneration, of course, it consumes much less, it will only be slightly above 2000 watt hour it will consume in 10.7 kilometer, I can calculate it is 191 watt hour per kilometer. I have also calculated the torque, and that comes from the numbers that we saw. For 12% slope at 30 km per hour, at 30 km, I should have written at 30 km per hour, the force required is 4000 newtons. That number is there in our calculation, 4000 newtons, and torque requirement goes to 1630 Newton meter. Very difficult to design such kind of motors with gears, we will bring the gear later on, will require a high gear ratio, 1630 Newton, otherwise motor will not, electric motor will not be able to give you. But I had also added that starting torque, 20% slope, that is 11.3 degree slope. Remember, I had told you how to convert the percentage slope into degree. The torque required is 2700 Newton meter. Wow! And torque is independent of velocity. So, even at 0 velocity you require the same torque. Plus, even for 0.2 meter per second acceleration, to just get it moving, you are not bothered about the speed at that time, get it moving by 0.2 meter per second, that is an acceleration. You require another 700 Newton meter. So, you require almost 3500 Newton meter torque. That is going to be not easy, and that is something you have to worry about when you design a motor. So, summary of the pickup truck, it is a low end pickup truck. We actually find that since it consumes how much energy? It consumes about 250 watt hour per kilometer. So, if I have a 200 kilometer, I require a 50 kilowatt hour battery. I may require slightly excess, because I am not taking into account the inefficiencies. So, 55 maybe 50, 60 kilowatt hour, as 85% is used, and finally, it goes to 80% because the battery deteriorates, and still it should give me 200 kilometer. My requirement goes to 75 kilowatt hour. I will look at this 85%, 80% number in greater detail later on. Now, remember that 75 kilowatt hour itself will add 400 kg of weight. So, my total gross weight has to include this. If I have a smaller battery, 50 kilowatt hour, it will be less. So, we have to compromise, we have to figure out. Computations carried out without taking motor and control inefficiencies, which could add another 15% weight and size. So, the motors and controllers will be better designed. So, you get good efficiencies, but 15% size. Torque requirement is about 3000, a little more than that, 3500 at 20% slope. Single gear may be very difficult, and yet one might try to do it with single gear. Otherwise, one has to do gear change, in which case you have to have a clutch which disengages the gear and then go to another gear. Remember that high slope when you are trying to climb up. Maybe just for that you may have one gear. For acceleration, you probably will manage. This is what will be required. So, let me come to the conclusion of vehicle dynamics. I have done that over last 4.5, 5 hours. One more thing that I actually did, after we computed this energy efficiency, I took this sedan and say, what if I vary the drag coefficient? What will happen? I have taken here mu to be 0.006 and I have varied the drag coefficient. As I vary the drag coefficient, I see the watt hour per kilometer significantly varies. If my drag coefficient can go down to 0.25, then my energy requirement is only about 62, 63 watt hour per kilometer. This is assuming R equal to 0.5 regeneration. On the other hand, if drag coefficient goes up to 0.5, then it goes significantly high to almost 85, 90. So, one has to be very careful, each of the parameters, sensitivity, this is called sensitivity analysis. I have to be very careful that my CD does not go up, CD is as low as possible. Similarly, I look at fix a CD and start varying the mu, the rolling resistance this time. Now, remember that you can't do too much about the area, it was CD into area. So, area you can't do too much, CD is one thing that you can change, and the other thing is this is not as bad, but even here it goes to 70 to 90. Well, here it goes from 60 to almost 88, 890. Here it goes 72 to 90, and again I had taken mu to be 0.06. If I increase it, it can get very bad. If I reduce it, it can go down. Now, this means value of a tire. Remember, somebody will say, well, it will add 2000 rupees extra for, or all the tires, there are so many tires. In a sedan, there are only 4 tires. It will add 5000 rupees. But if 5000 rupees will give me 10 watt-hour per kilometer reduction, you can just compute. In no time, in a year, you can recover that cost. This kind of optimization becomes extremely important for electric vehicles. Your battery size can go down, your that means capital cost can down, and of course, energy will also go down. So, this is something that I talked about. This is with R equal to 0.5, and with 100% regeneration it is much better. Now, so far I have not talked about torque, though I did compute torque. The importance of torque we have not talked about. Torque is required, one is in acceleration, again in the slope, and you will repeat it why we have computed it. So, you will find it that this is a major issue. As speed becomes high, power requirement goes high. Torque remains more or less constant, does not depend on speed. So, on the one hand I have to worry about torque, otherwise I have to worry about power at high speeds. At low speed, power requirement is not large. If you saw the number below 50 kilometer, 60 kilometer, very little. Once you went to 80, 90, it went up. So, power requirement above 60 kilometer per hour you have to worry about. If you go to 100 kilometer per hour or 130 or 150 kilometer hour, your power becomes very high. Do not forget, power is a cube of the velocity. So, correspondingly your energy requirement will also go up, the battery size will go up. So, besides torque and power, the other critical thing that has to be one has to worry about is RPM, because RPM will give you what is the speed at which you can go. You can design for power and torque to go to 150 kilometer. If your RPM does not allow you to go to 150 kilometer per hour, what is the use? Of course, both power, torque and speed, you can multiply torque, divide speed by a certain factor, by the gear ratio. Of course, if you change, if you have different gears, that is multi-gear, which will require a clutch and all that, you can use a different gear ratio, a smaller gear ratio when at high speed, and when you need high torque, you can have a higher gear ratio. But if you use a single gear, you have to balance between the two. We will learn all these things going forward. Energy required per kilometer and its impact. I have repeatedly pointing out, while we have learned to calculate it, we have not taken into account inefficiencies. If you take into inefficiencies, actual requirement is very close to what we computed. We just multiply by that inefficiency and you will see that. We also require in the battery, when we talk about battery, you will see there are two parameters. One is the total energy required, another is a peak power requirement. A peak power means you are trying to draw higher current from a battery, and as we learn, as we talk about battery, you will see higher current, drawing large currents also is a problematic, it impacts the life of the battery. So, we will look at what is called C rate, the power requirement also in greater detail. Motor controllers have to be defined for a certain output power and torque, and rather than input power. So, the input power could be whatever, and we have the inefficiency, that means the output power that I want. What we have all computed is output power. One other issue that comes up, if you have larger inefficiency in motor controller, your output power is much less than the input power. What happens to the rest of the energy, rest of the power? It actually dissipates as heat. So, thermal will become very important. What will you do with the? You cannot allow it to keep on getting heated up, you have to remove that heat. So, in motor and controller, that also will become very important. All the time so far we have not considered the auxiliary power and energy requirement in real vehicle, you will have to add this. I think the last thing that I want to actually look at, what should be the drivetrain voltage that I should use? Well, the one which is commonly used actually is 48 volt for small size vehicles, very common, 48 volt. These have more or less become standard throughout the world. For 2-wheelers, 3-wheelers, 4-wheelers in the marginal, 48 volt is not good enough. For in India, some 4-wheelers are defined at 72 volt. 72 volt is not a standard in the world, it is more used in India. 48 volt is very common. As you go higher vehicle, cars, you tend to go to higher voltage. Why? Because for the same power, if voltage goes high, current goes down. If voltage is small, 48 volt, your current will be 200, 300 amperes. Any time you have to use 200 to 300 ampere, first of all your battery should be capable of giving that, not easy, you will see that. Number 2, lot of heat dissipation, I square R loss will always be there. Even a conductor, he has a resistance, I square R loss will be there. Large current, I square. So, if you limit yourself to 100 ampere, you will get losses 100 square into R. If you go to 200 amperes, your actually losses become 4 times, and if you go to 300 ampere, losses become 9 times. So, if you go for higher voltage, your current can be smaller, and that is the reason for motors up to 75 kilowatt. This is used for motors up to 12 to 15 kilowatt. 15 kilowatt, you don't. 15 kilowatt itself at 48 volt is 300 amperes. At 350 volt, if I go to 75, I am still talking about slightly higher than 200 amperes. And for even higher power, you go for 750 volt, 80 kilowatt to 300 kilowatt. Now, of course, that 300 kilowatts you still have a very, very high current requirement of 400 amperes. But I have not seen vehicles going above 750 volt. So, these 3 are emerging to be standard: 48 volt, 350 volt, 750 volt. And everything will have to design, motor and controller has to be designed, battery has to be designed, your converters has to be designed accordingly. There is one more concept which will not deal with in this course. Can I use distributed motors? Can I use 4 motors on 4 different tires? My cost goes up, but can I increase my energy efficiency, use less energy per kilometer? Can I have more maneuverability? All this is possible. So, you will see more and more distributed motors instead of 1 motor driving the whole vehicle, maybe 2 motors, maybe 4 motors, and you will see that. Finally, what did we do in this chapter and why? An electric vehicle would have to have a motor and controller. We have for that computed what is the torque requirement. We have computed what is the energy power requirement for the motor. Battery will have to have sufficient energy. So, we have actually talked about what is the energy required to move a vehicle, go to a certain drive cycle, and at every instant it should be able to give give sufficient power to motor and controller. That is what we have tried to figure out. We have learned to compute power, energy and torque for different vehicles at different speeds, of course, at different speeds, and this is something that we will be doing more and more. We also learned the impact of various vehicle parameters like rolling resistance, aerodynamic resistance, vehicle frontal area, weight, slope, pickup acceleration, regenerative requirement on power, energy and torque, and all at different RPM. And we have touched upon, we have not really covered this, the impact of gear ratio, which I will actually do in the next chapter. What we will do, having done that, I am going to go to the overview now. Chapter 3 will look at the subsystems of electric vehicle, where we will also look at what motors and controller, what battery, what is the gear ratio that you require, what are the parameters for a vehicle and what are the subsystems. After that, in chapter 4, we will do fundamentals of batteries. Then chapter 5 and 6 will run concurrently, one on motor and controller, another is details of battery design, getting into the details of battery design. And then in chapter 7, we will talk about chargers and charging infrastructure, and finally we will end by talking about the overall what kind of management that you do when you try to run electric vehicles. Okay. I have completed this second chapter, which is a very important chapter, which actually helps you understand what is the force, torque, energy, power at different RPM for all kinds of vehicles. This, as I pointed out right in the beginning, would be done for even a internal combustion engine vehicle, petrol vehicle, diesel vehicle. More or less the analysis is same. We may use few terms like regeneration is unlikely to be there in a petrol vehicle, though today's petrol vehicle have an electrical battery and does a regeneration, because the transition is going on. So, that much is common. So, automotive engineer would probably already know that, but here I trained, we also got it for electrical, electronics, computer science, civil, aeronautical engineer to figure this out. One thing that I have not done, I have done all kinds of vehicles, 2-wheeler, 3-wheeler, 4-wheeler, trucks. Now, pretty much any other vehicle can be figured out. What I did not do is a boat or an aircraft. Both are vehicles. The mechanism is not exactly the same, but a very similar approach. Let me see at least if I can do something towards the end on an aircraft. Because a lot of UAV, a lot of youngsters are not designing UAV. What is the motor required? What is the battery required? At least you will figure it out. Okay. And want to point out that a good understanding of vehicle dynamics prepares ground for EV subsystems design. EV drivetrain requirements come from this: power, torque, speed and energy consideration at different RPM, different speeds, becomes very important. We have given a number of assignments throughout the chapter. Please do that. A lot of learning will come from those assignments. Thank you very much. Bye.